Hello and welcome back to the last talk on today's main stage. Before we start, I would just like to thank to our partners, primarily to TTC Teleport, which is the biggest data center in Central Europe where we are sitting right now, and also partners such as MSD, who have the awesome Labyrinth in 3D World. I hope that you already visited their stand, or Showmax and Microsoft. Our last talk today is by Ben Sandofsky, who's from the San Francisco Bay Area, and his app Spectre is the winner of iPhone App of the Year 2019, so you might know it. A fun fact about Ben is that he has a dog called June, whose photos they use in all the demo photos. So let's not waste any more time and let's go straight to the talk. After that, there will be, of course, questions. You can post them on Slido, and after that, we will sum up today's broadcasting. So let's go to the talk now.
Hey everyone, I'm Ben, and today I'm going to be talking about building a real-time video processor with Swift and Metal. Now, briefly about me, I'm co-founder of Lux Optics, and we build photography apps. Our most recent app, Spectre, was chosen by Apple as iPhone App of the Year for 2019, and it creates computational long exposures with real-time video data that's coming in from the device. Our first app was Halide, which is used for manual photography, and it still makes an excellent example for today's talk because we have a mode in there that's similar to portrait mode, and it's taking multiple video sources and blending them together to create a synthetic bokeh effect. That could involve the color data that's coming off the sensor and also the auxiliary depth data. And we're going to touch on this feature a few times in the talk because it makes an excellent example. Now, this talk today is broken up into three sections. I'm going to start by talking about the overall architecture of a real-time video app. I'm going to be talking about the important performance bottlenecks you might encounter, and then I'm going to be touching on the nuances and theory on working with color data. So we have a lot to cover, so we're going to get started right away. Let's talk about architecture. Now, I'm going to spare you a detailed line-by-line walkthrough with AV Foundation because you can read the docs. But at a very high level, you're going to hook into a delegate method in your AV capture session, and you're going to request from the system to receive video frames live as they come off the sensor. And then you'll receive callback method 30 or even 60 times per second with each frame as it arrives. It's up to you to build your core render loop. And so what that means is, as each frame arrives, you will update your internal state, which depends on whatever your app does, and then you're going to issue commands to the GPU to either further modify the image or to render it on screen. Now, the first part is going to be predominantly written in Swift, and the second part is going to be written in shaders, which are these tiny programs that execute on the GPU, and they're written in a subset of C++14, which is known by Apple as Metal. You can think of these shaders as executing massively in parallel, one execution per pixel on screen. So you can think of it as a massive number of threads executing all at once. Now, you have two choices for how you want to construct your GPU commands. We're going to dive into detail in the compute pipeline, which is a bit more straightforward, but there's also the 3D pipeline, which is the traditional pipeline that GPUs were built to manage. Now, the 3D pipeline is usually used for rendering a 3D game or for rendering in 3D software, whereas a compute pipeline could be used for any massive parallelizable problem. So you could use it here for editing images, or you could even use it for computing Bitcoin. So here's an example of a shader. Now, this is a hello world where we just take in one bitmap and we write that same bitmap value out to another bitmap that will be displayed on screen. Now, in GPU parlance, a bitmap is known as a texture. It's a little more nuanced than that, but we'll dive into that shortly. But we have a texture 0 and texture 1, which are bound to these two variables, in texture and out texture. We read a value from the in texture and we write it to the out texture. Now, how do you call the shader? Well, over in the app side of things in Swift, what you will do at app launch is that you will set up a state of the GPU, a compute state, where you'll say, I want to call this function, and you create a handle to this function. And then later, every time a frame arrives, you will tell the GPU, please set yourself into that state I set up earlier, that function I'm referencing. Here are the parameters that I want to pass to you, and then go dispatch it to the GPU, and then it'll be dispatched asynchronously. Now, looking back at that double bracket notation, that is the binding from the CPU side of things, the Swift code, into the GPU side of things. So here it's saying texture of index 0 should be bound to texture variable 0 in that Swift code I showed you just a moment ago. Now, the 3D pipeline is a little more complicated, and it's much more interesting if you're rendering a 3D scene, but it's still important to know because it is the most performant way to display things on the screen. Now, in a 3D scene, for our purposes, we are going to render the world's most boring 3D scene, which will be a square plane. So I'm going to pass 4 vertices to the GPU to render a plane, and then I'm going to pass a texture that will render on that plane as just a flat texture, similar to the hello world as earlier. Now, when this is dispatched over to the GPU, it's actually broken into 2 separate steps, because that's what you usually want to do when you're rendering a 3D scene. The first step is to modify those 4 vertices that I am sending over to the GPU. And this step is usually used where if you're handing it a 3D model, you need to do a bunch of matrix transformations to project it into your camera. A lot of details that aren't relevant today. But the second stage is most interesting, which is known as the fragment stage, where you render the actual surface on screen. So the vertex stage is rendered once per vertex that make up your 3D model, and then the fragment stage is rendered once per position on your surface that will then be rendered onto screen. Now, normally when you write a fragment shader to render the surface, you would implement some kind of sophisticated lighting algorithm so you could recreate a matte or a shiny surface, but for us, what's more interesting is that we're just going to render a flat texture out similar to what we were doing before, and it's that simple. Now, what's interesting with textures and working with the GPU is that it can perform certain operations with extreme performance efficiency. So for example, if you were on the CPU and you're just writing Swift code where you wanted to blend between 2 pixels, so say you have this checkerboard pattern and you want to render something that's halfway between this black and white value, you'd probably take these 2 values and write some bilinear interpolation, what have you, and it's up to your user code to implement it. But on the GPU, you can just say, sample these 2 positions, and the hardware will actually filter it for you and give you a simple blended value between the 2 points. So there are all sorts of affordances when working with the GPU that are extremely efficient. Now, why would you choose one of these pipelines over the other? Well, the compute feature is extremely intuitive because it's just writing general purpose code. But at the same time, if you are rendering something that's like a 3D scene, it's in your interest to use the 3D pipeline because it can take certain optimizations for you. So for example, if you're rendering the scene which looks like the group FaceTime, where you have multiple videos overlapping each other, you can have the GPU discard the portion of those frames that are occluded, that are not visible. So the GPU can be smart enough to not execute the shader for that surface that's not going to be displayed on screen. When you render something that's not ever going to be displayed, that's known as overdraw, and it's extremely inefficient because it's just wasted time, right? Now, you could implement the culling algorithms like in the 3D pipeline yourself, but then you're probably not going to do as good of a job as what the pipeline gives you for free. So if you're rendering something that feels like a 3D scene or involves sophisticated layering, you're probably really going to want to render a 3D scene, but in a 2D context. Basically, just render it as if it's a flat scene. Now, this talk is about Swift, so I'd like to touch on a couple nice features that you get by using Swift as opposed to C or C++. Now, the first thing that's nifty is that you can already in Swift import structs from C and get all the affordances of working with Swift, but ultimately it compiles down to vanilla C structs. And this is pretty nice because metal uses C-structs to pass data around. So if you're passing parameters to your shader, so you can still operate at a high level, use initializers that you're used to, all while you're in the Swift side, and then it gets boxed up into a convenient struct that you just load on your shader as if it's any other C-struct. So that's pretty cool. Another nice thing is the syntactic sugar that Swift offers. So if you noticed with Swift 5, for example, they added function builders. Now, this gives you a nice opportunity to build something like a domain-specific language for setting up those bindings that I showed you earlier. So rather than writing imperative code that assigns the parameters to the different slots in your encoder, here I can declaratively say I want to bind these values to these shaders, and it's much more intuitive to read than the code I showed earlier. So there's one last thing I want to touch on that hopefully I didn't gloss over too much, and that's the amount of data that's passing through in this run loop. Now, it's important to note each frame of a 12.5 megapixel image is not 12.5 megabytes, it is 50 megabytes, just a little under that. And that's because 12.5 times 4 color channels comes out to about 50 megabytes. So it doesn't take a lot of math to realize, wait a minute, the iPhone has less than 2 gigabytes of memory. And then when you factor in the system, you're really dealing with like maybe a gigabyte of memory max on current iPhones that you can work with before your app crashes. So that means that you just don't have a lot of buffers to work with. And if you start missing frames and your data starts backing up, then you're going to run into a crash. So it's extremely important in that run loop to, as soon as you're done with dealing with a frame that's coming from the system, release it back to the system so it can recycle it back into its pool. Similar to UI table view cells, but with much more dire consequences if you accidentally mess up on the recycling, right? That brings us to the second topic of today, which is dealing with performance. Now, performance is important because all the time you're going to be dealing with data that you have to process in a very short window. So if you're dealing with 30 frames a second, then you're dealing with about 30 milliseconds to do all of your processing before you start dropping frames. And here's an example with our portrait effect. The depth data that's given to us in the system, if we were to just display it on screen, would be this white clipped image on the right. When you expect something similar to the image in the middle that we would use to generate the depth map to synthesize the different depth of field effects, right? So the reason that the image on the right is what you get is that the system provides depth data in an unclamped format where each pixel represents meters. So you might have one pixel that's 10, so it's the image is 10 meters away, and then another pixel will be 0.5 because it's half a meter away from the camera. So the long and the short of it is, before each frame gets rendered, we have to go in and find the minimum and maximum values in the image in order to clamp it conveniently between 0 and 1. Okay? And a few years ago, I built a feature when I was contracting with Periscope where they wanted real-time drawing. And this is another example where we had to process a lot of data in a very short window, where as the user's drawing on screen, we're adding different points onto the image along with timestamps. Because a few seconds after you draw on screen, we want them to disappear from the screen. So that could mean having to iterate over thousands of points on screen in 30 milliseconds and updating timestamps. So even if you aren't going to be encountering either of those problems, it's really helpful to know where your bottlenecks are so you don't sweat the small stuff, right? And so I'm going to dive into what a lot of modern engineers don't understand about performance. It's very often you'll see in programming interviews, they'll talk about computational complexity and all these CS concepts while ignoring where modern bottlenecks are in modern systems. And in fact, CPUs have gotten a lot faster, but memory has not kept up with Moore's law. Your bottleneck in your program is most likely memory access. Okay, the system stalled while it reaches out to main memory to access data. Okay, now often it is hidden from you through a convenient architecture, which are known as memory hierarchies. So your desktop or even mobile system has a set of different memories that are located closer and closer to the CPU. And the closer you get to the CPU, the faster they are to access, but the less memory is available. Okay, I'm going to steal a demo from Scott Myers, who's a noted C++ guru, and I will link to him shortly. But this is an excellent illustration of the different speeds it takes to access a memory. So there's a very small amount of memory that's located right on the CPU, which is known as L1 cache. So as you access data, it is put into L1 cache. And as you access more data, it pushes out the least recently used data into a cache that's further away but takes longer to access. So let's say that it takes this long to access L1 memory. Once that fills up and it starts pushing data to L2, which is larger but slightly farther away, it takes this amount of time relative to L1. And then if that fills up, there's L3. And some systems even have an L4 cache. But if the data isn't available in these different hierarchies and you have to reach out to main memory, you might as well just go get a coffee, go check Reddit, because it is going to take an eternity relative to cache data to access it and do interesting things. Now, what are the different sizes of this data? Well, on the most popular iPhones in the world, not the current cutting edge ones, but the most popular ones, you're looking at about 64 kilobytes, that's with a K, kilobytes of memory that's in L1 cache, and that only takes 4 CPU cycles to access. L2 is 1 megabyte and takes 10 cycles. L3 is 4 megabytes and takes 40 cycles. And main memory takes that eternity of 120 cycles to access data. Okay, so the idea behind understanding all of these memory access patterns and then architecting your app to lean into these architectures is known as data-oriented design. And Scott Myers and Mike Acton have excellent videos. You can go find them on YouTube that talk about these different performance issues and false sharing and all sorts of these little gotchas. And I highly recommend checking it out. But at a high level, you want to think about your app in terms of data and the different transformations you're performing as you go through the app, and start there instead of at a high level of abstraction, as is typical in a lot of modern programming. Now, the good news is Instruments does have affordances to help you. There's the counters instrument that can help you figure out how many cache misses you're getting. But the problem is, this is not a problem that you can just benchmark away later. If you are not thinking about data access patterns as you're designing your app, it's very likely that you're going to run into something that can never be fast, short of ripping out all of your code and starting over. So it doesn't have to be complicated, it just has to be a level of awareness of how you're accessing the data. So as an example, and this is an extremely common one and a very simple one, let's say you have a matrix of bytes. Now, if you access the matrix of bytes in the wrong order, where you're jumping from line to line greater than 64 bytes at a time, right? Where you have an array of arrays, and you're jumping around that array at a full length at a time, you're not going to be able to take advantage of cache lines, where the data is pulled into your app 64 bytes at a time. And it's going to be very difficult for the CPU to predict the next set of data that it will cache in advance before you access it. So it's really as simple as just going in there and saying, all right, I'm going to access data linearly, which means calling the right nested loop to make sure that you're going in the correct direction that the CPU can prefetch the data. But it also has implications as far as architecture. So let's say that you're building an app like Stardew Valley, okay, and you have these different models in there that represent the different patches of land that make up your world. And you want to represent a wheat patch so that every so often the wheat grows a little larger. You might be incrementing this counter with every frame. Okay, now if you were to use the naive object-oriented approach to designing your app, you would start with a wheat patch abstraction, which is a class, and you would have a position property that's inside of this class that represents the X and Y position. And then you would have, and of course you wouldn't just increment this height property, no, you would call the grow method to update its internal state. And this is going to always be dog slow. Okay, now in object-oriented languages, you're very much going to run into pointer chasing because each object is allocated at basically a random position on the heap. So you can't iterate through each of these objects and know that all the data is available there in the same cache line. A lot of these languages encourage dynamic dispatch, like by default in Objective-C. And so that means that similar to the data cache, there's also the instruction cache, which operates similarly. And just at a design perspective, it encourages you to think about your data as discrete instances that make up your model instead of processing large batches of data in groups. Okay? Now, Swift is nice because it gives you explicit control over data layout, where you know that if you lay out a struct, you can be sure of the stride and the how you're going to be packing data together to make the most use of memory as you create an array of the data that you want to process at once. By default, Swift encourages static dispatch. So unless you opt into dynamicism, it is going to all be statically dispatched, and you'll be able to take advantage of instruction caches. And most importantly, it just encourages you to think about your problem in terms of values instead of these heavyweight abstractions and enterprise design systems, right? So what is the simplest design you could come up with? Well, this is a little too close to the metal, but you could just represent those patches of wheat as an array of arrays of uint 8. I mean, you still want to have some sort of abstraction on top of it, right? Well, the good news is there are patterns you can take from like C++. One of them is the strong type def pattern, where you just take those values and you just wrap them in a struct, and the compiler will optimize away the information so it still only takes up that value in memory instead of the whole class and having to do pointer chasing at runtime. Now you're saying, well, wait a minute, what about shared behavior? Well, how will I survive without subclassing? And a classic example is polymorphism. So let's say you have a game and you have this Koopa, and you want to add the ability to fly. Well, what you'd normally do in an OO system for starting out is you would subclass that Koopa to make a flying Koopa, right? And then as you add more behavior, you might subclass that subclass and create a rich hierarchy. But then you run into a wall where, let's say you now have a Goomba that can also fly. Oh, what do you do here? Well, you could do multiple inheritance, but that's the road to insanity, right? And this is where you get into the phrase favor composition over inheritance, right? Where you create these different components and you contain them inside of the class, and then you can mix and match these different behaviors in these different classes. And that's a really good starting point for creating a well-factored app that doesn't have a crazy class hierarchy. But then in games in the last 10, 15 years, there's been a movement toward a pattern known as entity component systems, where instead of thinking about things as objects and subclasses, you break it into 3 types. There is the entity, which is the thing. Everything's an entity. A power-up, an enemy, a character. Everything's an entity, which is just a unique ID. It doesn't contain any behavior, it's just an identifier. Then you have the components, which is the data that are associated with these different features. So, for example, you might have, if you have physics, you might have mass, velocity, gravity. For the health system, you might have health that can take damage. But the data is isolated from the entities. Finally, the actual behavior is known as the system. So you would have the physics system operate on velocity. You would have the damage system operate on health. And this is a very powerful way of structuring your app because it's very easy to mix and match these different concepts. You could attach wings and have a flying power-up. You could attach wings to the main character and have a flying power-up, right? Or a flying character. And so it's very easy, especially as you're prototyping new features, you can just mix and match them without having to rip apart your class hierarchies. And that's incredibly powerful and makes you incredibly productive. But even if you want to stick to traditional class-oriented systems or however you're designing apps right now, the main takeaway is to think about data-oriented design as a way of thinking. So here's a concrete example. Let's say that we have an image that we want to blur. And you might know that a Gaussian blur, which is that beautiful rich blur that you'll see all the time, unfortunately has computational complexity of big O of n times r squared. Now, what does that mean? Well, it takes longer to execute based on the number of pixels, n, and the radius of the blur. The more blurrier you want it, it scales at r squared. So it gets very slow very quickly as you make the blur larger. Now, one solution is you could use a different algorithm than a traditional Gaussian blur. There are approximations of the Gaussian blur that are almost as good and can scale in linear time. But here's another simple technique. You can also mix and match it with a better algorithm. Why don't you just downscale the image to 1/4 of its size and then blur it and then upscale it? And that results in 1/4 the number of pixels you have to deal with, and the blur radius is going to be a fraction of what it would be normally. And here, if you look at these two images side by side, you'd be hard pressed to tell which one is a true Gaussian blur for most uses. So that brings us to the end of performance, and now you've got your app working, you've got images displaying on screen in a performant way. It's time to finally see all the labors of your hard work. And you expect when you're taking an image of this flower for it to look like this, but then as you've written your shader and you display it on screen, it ends up like this. What's going on there? It's almost as if there's only one color channel that's being given to your app. And well, it is by default. So when you ask for frames from the system, they are going to be encoded not in RGB with 3 color channels, but in an encoding known as YUV. And that's where the first channel is the luminance, that's the brightness value. And the next 2 channels are the amount of redness and the amount of blueness. So that's the hue that makes up the image. Okay, so the Y and the U and the V. With the U and the V representing the different positions on this chromaticity diagram. Sometimes you'll see those values represented as CBCR, which means color blue, color red. Okay, so why does Apple or most systems encode video like this other than to drive you mad, right? As I said earlier, the most important aspect of performance is going to be data. And by encoding images in this format, you're going to be able to pass around a fraction of the data. Let me explain how that is possible. So, you may have already seen this optical illusion passed around on Twitter, where from a distance it looks like this photo of these kids. Each of these kids has a different colored shirt. But then if you zoom in, you'll see that actually these shirts have this crisscross pattern of color, and your eyes are filling in the blanks and making the different shirts a different color. And this speaks to an optical illusion. Our eyes are much more sensitive to differences in brightness, which is luminance, than they are to shifts in color. So what's interesting is that you can take an image like this, and you can actually store a smaller version of the color data, and then at render time, upsample it, and most people are not going to be able to tell the difference. This is known as chromatic subsampling, where you basically store a fraction of the color data, all the luminance, because that's what's your eyes are most sensitive to, and then at render time, you only combine a fraction of the color data to get the final image. Humans are not able to tell the difference. And the good news is that you don't have to write a sophisticated algorithm to reassemble it. In fact, inside the ARKit source code, inside the code examples linked to at the bottom, you could just copy and paste the shader. It will run a performant matrix transformation to give you these RGB values at render time. For whatever reason, Apple does not include the sample code in the actual metal docs, but it's very easy to just copy and paste this and call it a day. Now, there are all sorts of different numbers that are attached that represent the different types of subsampling. So 444 means that there's no subsampling. Every pixel of luminance corresponds with a pixel of color, but you're frequently going to see 420, which basically means 1/4 of the color data that you're expecting normally. And it's worth a Wikipedia dive to fully understand what these different numbers mean. But this brings us to this magic constant that you're going to see inside the docs, where you can ask for different color formats. You can ask for 32-bit BGRA, which means a full color image. But in order to access a full 4K image from the sensor, it is only available in the subsampled format. Its constant is known as 420 YPCBR CBCR 8 biplanar full range. So the 420 refers to how subsampled it is. The YPCBCR refers to the fact that it is a YUV image. Okay? Now, this is difficult to keep straight in your head, and it would be very easy to get this mixed up at render time because the textures that the system gives you are not type safe. So it will hand you a metal texture that has a bunch of bytes in it. Is it RGB data? Is it YUV data? Well, you could look inside the pixel format if it's available, and it'll give you a hint. But it's very easy to get them mixed up and to render a YUV image in a shader that doesn't support it, and then you waste an hour trying to debug something and you're like, oh, I forgot to write a YUV shader. So what I end up doing is I write a lightweight wrapper, which is a struct, and I combine that with an enum. So every one of my image processing functions can accept either YB or YCBCR, or they can accept a BGRA. And this way I know immediately, oh, I forgot to implement a corresponding version of the shader that accepts the different image format, right? So that's great. So we've solved this, we're recombining the image, and then we see, oh, it's awfully dark. What's going on there? Well, this is the second issue, and it is the bane of beginning graphic engineers. And I promise I will not scare you, but it's time to dive into gamma. Okay. So what is gamma? Well, let's say we're imagining a linear gradient, a smooth gradient that goes from pure black to pure white. And this is probably what you would think of as a linear gradient, where, you know, right at the middle is halfway between 0 and 255. So you're thinking like the 128 value is right in the middle, right? Well, in fact, if you wrote a for loop that just iterated and printed on screen these linear values between 0 and 255, it would actually look like the gradient on the top, okay? And this has to do with, again, the human visual system. Our eyes are more sensitive to shifts in shadows than in the highlights. So what that means is that the bottom image is not actually a linear gradient. It's kind of skewed toward the dark end, where its 128 is way over on the right side. Okay? And that leads to a problem, because then if we try to publish a perceptually linear gradient, we don't have enough bits on the low end to represent it without ugly banding. So in case you can't see it well on the screen, the middle and bottom gradient here are the same gradient. I just boosted the values to accentuate the issue with banding. But basically, there just aren't enough bits over in the shadows to represent those really dark shadows, but there's more than enough bits to represent the highlights. So what can we do to solve this? And this is why you'll use a gamma curve. So in a nutshell, when you take an image with your camera, the values that are read into the sensor are linear. So they just get brighter and brighter in a linear fashion like you're expecting in your mind. But because 8 bits isn't enough to represent all that data, before we save it to a file or memory, we apply a curve to sort of push the values up, and then we encode it so that there's more bits available in the shadows. And then when we go to display it on screen, we apply the inverse curve. By we, I mean your monitor, your operating system applies an inverse curve to make it look appropriate. Okay? Now, it's really important to understand this concept. Although to its credit, a lot of it is magically abstracted away. If you aren't having to do image manipulation, you'd never know about gamma encoding. But as soon as you start having to do a combination of pixels and the math, you're probably expecting linear values, where if you take two color values and say, give me the average of the two, you're expecting to be correct. And there's all sorts of odd bugs, and I recommend checking out articles like this one, Gamma Error in Picture Scaling, which shows this example image, which it was very common years ago for image editors when they downsample them to end up with this gray square in the lower right when you're really expecting the image in the upper right. And this article goes into detail about where the folly in the math lies. But even apps like Photoshop, for the longest time, had gamma bugs, like with a brush blend modes, where you'd see these dark fringes, like in the bottom part of this image. And in fact, artists were so used to these artifacts, Photoshop had to put in backward compatibility where it could still reproduce these issues. And then artists would check a box like to turn off the backward compatibility and get the blending like you'd see in the upper part. It's all too common in font rendering when it comes to anti-aliasing. You end up with darker images than you're expected because, again, the way that they're being averaged together. So I highly recommend checking out what every coder should know about gamma and fully understand it. Otherwise, it's going to cause a lot of frustration and confusion down the road. The most important lesson is when you're running into these weird issues where things are too dark or too light, don't fix it by tweaking values. If you're starting out in 3D rendering, it's pretty common where people will be like, oh, this light is too dark, so I'll just crank up the values, when in fact it's a mistake in their gamma calculations. The good news is Apple, here in the Metal Programming Language Guide, they provide a shader sample. You can copy and paste to gamma encode and gamma decode it, but it's still up to you to understand what's going on. Cool. So you've got that solved. You've got the image rendering with the appropriate brightness. And then, if you have a sharp eye, you might notice something like this, where the color is just slightly off. Okay? And what's going on here? And this is a recent problem with modern displays. Well, it involves color spaces. So, what is a color space? This horseshoe-like shape represents the entire human visual spectrum. So this is everything the human eye can see. And this triangle in the middle represents the area that most monitors in the world can actually render, which is just a subset of the human visual system. No monitor in the world can render this entire horseshoe. Okay? Now, the problem is Apple went and improved things by releasing displays that support a wider range of colors. They call Apple P3. This is similar to DCI P3, which is integrated in cinema, where there's a much wider gamut of colors that are now renderable. But all of the images are encoded very often, especially on the web, assuming that they are located in that smaller triangle. So what ends up happening is, let's say that you have RGB values that are expecting that small triangle, and you go to render them, and they get plugged into those locations in the larger triangle. Everything is going to be shifted around, your hues are going to look wrong, and you're going to run into all sorts of issues. Or vice versa, your images are going to be much more muted because they're being crammed into a less saturated color space, right? And the good news is, it is not complicated to move from one color space to another once you're aware of the different color spaces you're working in. You just have to copy and paste different matrices, and you do a multiplication, and everything renders properly. But knowing is half the battle. So this is why in that enum and struct that I showed earlier, I also include data about the different color space I'm working with. So if I recognize that I'm getting a wide gamut image coming into the system, then I need to perform a matrix transformation at render time. And it's important that as I'm doing calculations, there's the idea of the working color space that you're going to be doing all of your math in. So as I'm rendering an image on screen, I am doing everything in display P3. So similar to if you're working on the server side and your sysadmin needs to pick a time zone, you always pick UTC. But if you can't, make sure at least everyone's picking the proper time zone together and everyone's on the same time zone. Otherwise, if it's inconsistent with all of your math, then you're going to run into all sorts of difficult to debug issues. So my recommendation is to transform your images into display P3 and do your math there. What's interesting is down the road, right now we're working on 8-bit images, so there's a trade-off where hypothetically it's better to do sRGB images in 8-bit and use an sRGB color space, because then you don't have to worry as much about banding. We're now approaching a point where images are going to be encoded in 10-bit, which gives you more than enough bits to work in color space so that you don't see ugly banding and you don't see artifacts. But that doesn't mean that you're not going to run into issues with gamma, right? Even with 10 bits, meanwhile, we're dealing with HDR displays that are going to take full advantage of those full 10 bits. So it's still up to you to understand how gamma encoding and these color spaces work, because they're not going away anytime soon. So we covered a lot in today's talk. We talked about the render loop, which is the most important bit of your app that you're going to be implementing. And if you want to find out more about that, I highly recommend also checking out different game programming tutorials. They talk about the game loop, which is a similar concept, although in that case, the run is going to be dictated by a timer instead of frames coming to the system. But I highly recommend checking out different game programming tutorials if you want to bring yourself to the next level there. And similarly, you're going to find out a lot about shaders, which we talked about and showed different samples of code there. And I recommend checking out, brush up on your C++. If you want a cross-platform solution, you might want to check out Vulkan. A lot of people ask me if it's worthwhile to study OpenGL now that there's Vulkan and Metal. And unfortunately, OpenGL can be challenging because it has about 20 years of legacy information. So you're probably, if you're starting off today, there are so many good resources in Metal, and it's not nearly as complicated as Vulkan. So that said, a lot of these concepts now are compatible with Vulkan, and I find myself now studying different tutorials around NVIDIA's GPU programming language, CUDA. So once you understand this in one platform, it's not as difficult as you'd think to port it to the different systems because they all use very analogous constructs. So check out Vulkan, check out CUDA. They're all more similar than they are different. We talked about data and data-oriented design, so I recommend checking out the different talks by Mike Acton as a starting point. There's an excellent tutorial, Data-Oriented Design is the Future of MMORPGs. It's published in 2007, but there's now a variety of different articles on data-oriented design that are within Google's reach. And finally, we talked about the theory, which is YV, gamma, and color spaces. So if you want to find out more about that, I recommend a book, Real-Time Rendering. They recently published the 4th edition. On the cover of that book is an image of a Star Wars stormtrooper. And it provides a lot of information, not just about 3D rendering, but about a lot of the theory, matrix transformations, color spaces, and a lot of the history. So it's an excellent, although about as dense as a textbook, introduction. And that's pretty much everything I wanted to cover today. So if you have any questions, I'm available in the networking section of the conference. But thanks for attending, and hope you have a good day. Hey there.
Hello. Thank you, Ben. That was really nice. So let's switch to questions right now. Actually, we have one question.
Mm-hmm.
What is that gray triangle around the smaller one?
Uh, which gray triangle around the smaller one? I'm not sure what you're referring to.
Maybe in the where you were showing the colors at the end now.
Mm-hmm. In the color space diagram, maybe?
Probably, yeah.
I don't know. I can't think of a great. So I think that was just a way that they were representing the different color the spaces and how they overlap. But the triangles themselves, like the color within the triangle, doesn't really matter. The triangle represents, like on a map, the territory of the different color spaces. So Display P3 is slightly larger than sRGB, so it's going to contain all of the images that are a superset of sRGB. And yep, the smaller one is just sRGB. So I wouldn't worry too much about specific colors in there. In fact, that whole image or the slide around color spaces is kind of a lie, because I said that they represent all the colors in the visual spectrum, but you're displaying it on probably an sRGB monitor. So it's by definition not actually displaying all the colors that are visible, because no monitor can display it. So, yep. Cool.
Okay. Oh, actually, another question just came. Uh, is DoD relevant for CRUD app development, or is it something that's reserved for game development and visual processing?
That's a good question. I'll say off the bat that most software probably written in the world doesn't need any kind of adequate performance. And most of your performance problems, you're not dealing with high traffic websites. You're probably dealing with high latency anyway on the web, right? Unless, so if you're already looking at like a 1 second round trip on your web service, then, who am I to judge whether saving, a few milliseconds here and there makes a difference? I will absolutely say that at scale it matters. So, for example, if you're designing a database, understanding how your data is laid out and understanding, like, well, if your columns are compactly stored in your database, if you use, well, here's a good example. If you store a value as a bit field, you can fit 8 different booleans inside of that bit field and only take up one single uint8 column in your database, right? As opposed to having 8 separate columns that are all booleans. Depending on your database implementation, that could be 8 whole bytes that are wasted on a single on or off value, right? So certainly, I would think that if you're going to be designing a database schema, you should absolutely understand the underlying data. Yeah, so and it's kind of funny because a lot of people, they say that, like, well, your data is I/O bound, right? Where you are paying in round trips, but at scale, yes, very often what you're able to pass through your system is going to affect performance. When you're talking about when you're talking to 2 systems inside of a data center, then yes, suddenly you are going to be CPU bound and you need to understand how that's going. But I'd say that even if you aren't caring about the performance side of things, that data-oriented design is a way of thinking outside of this fad around object-oriented programming that dominated programming in the early 2000s, and we're starting to sort of get away from with like Golang and with Swift, which emphasizes value types. So there's just the academic reason to try something that you're not comfortable with. So yeah.
Thank you. Another question is, are there any good links for AV depth data stuff regarding lens correction? And
Mm-hmm.
the person
So,
says, I'm developing a computer vision 3D reconstruction using Face ID app.
That's a good question. The exact talks at WWDC, I don't remember the exact numbers, but the last few years they've had, starting with capturing depth data in your photos and depth editing. So ever since the iPhone 7, or I think it might have been 7 or the 8, when they introduced the APIs, they've had several very useful talks from Apple, including one talk that talks about lens correction. And for the people who aren't familiar with computer vision, basically every lens has a built-in barrel distortion. So like it's like you've seen this on the ultra-wide lens is an extreme example, whereas you get closer, like the features are distorted and warped, right? And so Apple actually provides a lookup table so you can unwarp the curvature of your image and get what's known as a rectilinear image, which is much easier when you're in a computer vision application. You want the rectilinear image rather than all these distortions because it messes up your data. So the short answer is that there is an API which provides a lookup table, and they even provide, I think, sample code in the header for how to look into the lookup table and correct your image.
Thank you. And the last one is not a question, but it's praise. Excellent talk, by far the most interesting today. So
Well, thank you.
that's
Thanks.
great. It was real interesting. Thank you very much, Ben. And now I would like to ask you to go to the 3D world to talk to our attendees for 15 minutes, or actually right now, because this was the last talk of the day on this stage, you can stay there as long as you want.
Cool.
So I hope you've enjoyed this. For our attendees, please rate this talk in Slido. Thank you very much for watching. Today we've had almost 600 people watching us, so that's great all around the world. So we are really excited. We will continue tomorrow at 12:30 Central European Summer Time, so stay with us. And we are looking forward to tomorrow. Thank you again, and see you tomorrow.
Thanks.
Bye.